Okay. Okay. So do we have any questions from the material that we discussed by now? Anything about Poisson process? All right. So we'll continue with our discussion of Poisson processes. We'll be looking at a couple of more examples and several other important properties of Poisson process as well. So you remember, well, we typically start with the Poisson process X. Okay. And I'll assume that this is an homogeneous Poisson process with rate lambda. Okay. A constant, a positive constant that we know. Right? And last time we agreed that we will denote by S1, S2, and so on the inter-arrival times of the events that this process is supposed to count. Okay, and then we also use W1, W2, and so on to denote the arrival times themselves. Right? So W, you may think W as any one of them is the waiting time until the end event happens. Okay, and last time we learned that these are waiting times, right? Okay, let me write it like that: waiting times. Okay, or maybe I should just specialize to one of them so that I can write the density as well. Okay, the end waiting time Wn has gamma distribution and we write that the Wn, right, the end event time is somewhere near time t with probability what? So just before time for this event to happen, just until time t, right? We must have n minus 1 arrivals. Since we are dealing with a Poisson process, we know that we can write that as what? Its probability is going to be lambda t times lambda t to the power n minus 1 divided by n minus 1 factorial times e to the minus lambda t. Right? And then in the next dt units of time, we expect to have one event to happen, which can be whose probability can be approximated by lambda times dt. And we also said that these inter-arrival times, S1, S2, and so on, are independent and identically distributed exponential random variables with common mean 1 over the rate of the Poisson process, right? 1 over lambda. Okay, and in a numerical example, we have also seen that we have seen actually a concrete numerical example of the following statement. We said in general, we know that for every u and t and integers k and n ordered like this, k being less than or equal to n, okay, if you want to calculate the conditional probability that there will be exactly k arrivals until time u, given that there are, or actually now u comes before t, given that you already know that there are exactly n arrivals in the interval from 0 to t, what is the probability that there must have been exactly k arrivals in the first u units of time? Okay, and we can write it like this equals to n choose k times u over t to the power k times 1 minus u over t to the power n minus k. Okay? we can quickly derive this more general statement. Okay, we look at this and by using the definition of conditional expectation, conditional probability, right? We can write the left-hand side, namely this, is the quotient of two probabilities. Right? In the numerator we have the probability that number of arrivals until u equals k and number of arrivals until time t equals n divided by the probability that number of arrivals until time t equals n. Right? And now these are not independent, but then we can again use the independent increment property here if we can write first of all this event equivalent in terms of the number of changes, the number of arrivals over disjoint intervals. So we have 0 here, time t here, u is somewhere in between, right? U is somewhere in between. For us to have k arrivals here and n arrivals here, we must have exactly n minus k arrivals here. So we can equivalently write this event, therefore the probability itself as what? The probability that this equals probability that number of arrivals until u equals k, and number of additional arrivals between time t and time u equals n minus k. Right? And then, okay, we copy this first.
X t minus, yeah.
So my u and n sometimes just get mixed up. Yeah, you better warn me so that we don't make a fatal error. Okay, this is supposed to be u as well. Okay. All right, then we don't have much space left over there. Let me just continue from here. Okay. Now, what do I know? Now, we know that this is basically number of arrivals from time u to t. So, over this interval, this is number of arrivals from 0 to t. So, these two intervals are disjoint, therefore, the number of counts are independent random variables. Therefore, the joint probability can be written as product of probabilities, right? So, xu equals k times the probability that xt minus xu equals n minus k. N minus k. Okay. Divided by the probability that number of arrivals till time t equals again n. Now we use here independent increments property, right? Due to independent increments of Poisson process. And then here we'll use the fact that this random variable, number of arrivals until time u, has a Poisson distribution, right? With mean lambda times the length of the interval, which is u, right? Similarly, this counts, right? Number of arrivals over the interval from u to t, which has length t minus u. Therefore, this has Poisson distribution with mean rate, number of arrivals per time unit, right? Times the length of the interval over which we are counting the number of arrivals. Okay, we have that. Therefore, now this becomes lambda times u, the mean of Poisson, lambda times u to the power k, right? Divided by k factorial times e to the minus lambda u, the mean of this Poisson, times here we have what? So this is the mean now, lambda times t minus u, mean to the power n minus k, divided by n minus k factorial, times e to the minus lambda times the length of the interval again, which is the minus u. Here we have the same, we can use the same result, which says now this is Poisson distribution with rate lambda times t. The probability that it equals n is lambda times t to the power n divided by n factorial times e to the minus lambda t. Then several cancellations will take place, right? So you have minus lambda u here, plus lambda u here. They cancel each other, I mean this part. Then you have minus lambda t, which is the same as this one. So this thing takes care of t part. Okay? And then lambda to the power k, lambda to the power n minus k gives, they give together lambda to the power n. You have lambda to the power n here. So lambdas cancel each other. So the result will not in fact depend on lambda. So independent of how frequently the arrivals may come, if you want to know what happened in the past, given what you know, what happened until this time, it's going to be independent of that lambda. And then we can just rearrange. Now there is this lambda n factorial, which will go all the way up. Then you divide by k factorial n times n minus k factorial times, now u to the power k, t minus u to the power n minus k. So bases are different, but at least the powers sum up to n. You have here also the n power of t. We can just split it into k and n minus k, distribute them, or match just the right number of powers with each one of these terms. So if you divide by u by t, you just get u over t to the power k, let's say. And then I just match the remaining n minus k powers of t with this, and then divide. T minus u over t will give you 1 minus u over t to the power n minus k. Okay? Okay. And we know that this is nothing but just n choose. Okay. Okay. And then, of course, we recognize that this is what? This is, well, probability mass function, right, of a binomial distribution, right, which is the result of, right, repeating n independent experiments with binomial with n Bernoulli experiments. Well, we should say with n independent Bernoulli experiments, just to remind you how we actually, how you typically get a binomial distribution. With n independent Bernoulli experiments, right, with success probability in this case, what is it? U over t. That's true. And how did we interpret this result? So you see, what could the experiments be in this case? So we look at the question itself. What did you start with? So n, right, is the number of experiments, right? So in each experiment, then what are we doing? In each experiment, right, we check if, right, a given arrival falls in time interval 0u. If this really happens, then that's a success for us. This is when a success happens, namely if arrival indeed falls or comes before time u, right? Right? We check, or maybe in each experiment we check if this happens, right? Which may happen, or which happens, right? With what probability? We just read from this line with probability u minus t, right? U being the length of the interval into which we are wondering if the arrival really falls, right? And the t is the entire length of the interval for which we know exact number of arrivals, right? We are already told that there are exactly n arrivals, and then, of course, for each arrival there are only two possibilities. Either that arrival must come before time u, or it must come between time u and t. Right? And this result just tells us that, in a sense, condition on the number of arrivals, the time of the arrival time has not only exponential distribution, but a uniform distribution. Right? It is uniform distribution because the probability is proportional to the length of the interval. Right? You are interested. Actually, this is a little too soon to say that we have actually a stronger or more precise statement of that result, but this kind of gives a hint for what is about to come. Okay? That's the interpretation. That's how you can interpret the result. Maybe that may also help you remember that in that way. Okay. And now, by now we have learned a couple of things, right? So inter-arrival times are independent identity distributed exponential random variables, therefore they have memorylessness property. And then we have the gamma distribution, or the gamma distributed arrival times. And then we have this conditional, when you condition on the number of arrivals, then in a sense you expect now the arrival times to have a uniform distribution as well. And we'll use some of these to solve problems like this. So this is an exercise, well, it is exercise 3.7, I guess, coming from your textbook. It is on page 295. Okay. And okay, according to this question, customers arrive at the facility according to a Poisson process with rate lambda. And by xt, we denote the number of arrivals. So this is number of customers, right, arrived until time t. Okay, and as usual, we will denote by W1, W2, and so on and so forth the arrival times of the first, second, third customers. Okay, these are all arrival times. And the question is what? They want us to find the conditional expectation of the time of the fifth customer. So, given that until time t, you already know that exactly 3 customers have arrived. Okay? So on average, when do you expect that the 5th customer is going to arrive if you already know that exactly 3 customers entered this facility until time t? Right? Any guesses? Or any answer, perhaps? Huh. So yes, so till time t, there are 3 customers have already arrived. We need to kind of determine how much time does it take for 2 more customers to come to the system, right? Okay, so maybe a picture is gonna help, right? So there is time t here. I have exactly 3 arrivals here, right? And that means the 4th arrival must happen after time t, first of all, perhaps here. And then there will be the 5th arrival. So this is W4, this is W5. And we would like to know the expected value of W5 given that until this, whatever time t is, right, there are exactly 3. Right? So the first guess is, of course, W5 itself is greater than t, so expected value conditional expectation should be greater than t. Right? But what else? What else? Well, first of all, this consists of what? So this is the 5th inter-arrival time, which is independent of everything else. Right? And unfortunately, I don't know where this starts. Perhaps there is the 3rd arrival time, which I know actually. Right? The 3rd arrival must have happened before time t. So there is this 4th inter-arrival time, right? So in principle, what should I do? I should be able to calculate the excess time, remaining time. So I am at time t. Right? I counted the number of people who entered the facility. Now, at time t, I should somehow guess how much more time we need to observe that the fourth customer is coming in, right? Because I already know that this many units of time nobody showed up, right? If it is useful at all to know that, then I should use that to guess how much more time left, plus just another inter-arrival time, right? Okay. But then you know what? You look at this one, inter-arrival times, right? For example, S4, S5 are just two of them. First of all, they have independent and identically distributed, right? And have exponential distribution, right? And what do we know about exponentials? They don't remember, right? So you're standing at time t here, right? Perhaps the fourth customer, you would think that they would remember that he has not come yet there, right, for so many units of time. But when you just tell him or her that it is now time showing t, he all of a sudden forgets that how far it passed since the last customer has arrived. Therefore, actually, the remaining time here is going to also have exponential distribution. Right? And then you would expect that this is actually expected value of full S4 plus, of course, S5. So there are no questions about S5. What is kind of surprising is that even that you know that there was some time left without any customer showed up until time t since the arrival of W3, right? You're still starting at time t. You treat as if just the third customer has just arrived at time t, and then you have a full inter-arrival time in front of you until the fourth customer comes, right? So that should be the answer, okay? And you will get accustomed to thinking like this, I hope, over time by effectively using the memory license property of exponential distribution. But otherwise, I guess you can still just argue a little bit deeper than this. And you may just say, okay, I would like to work with inter-arrival times, but for that to happen, I should somehow know the value of W3, the arrival time of the third customer. Even though you don't really know what it is, but we can then use the properties of conditional expectations to condition on that. To conditional, huh?
Don't we add time t to that expected time?
Say it again, x time t? X at time t?
We know that t time has passed. That's why shouldn't we add?
Oh yes, you are right. So this is actually how much time will pass starting from time t, right?
Yes.
So this is actually how much more time we have from time t. That's a good point. So we should add t because we are looking at the absolute, whatever, the length of wt. That's true. Thank you very much. Yes, that's true. But if I just put everything in the same order as time progresses, so I have t plus expected value of S4 plus S5. And which is what? T plus, what is the expectation? These expectations, or what are the expectations of W4 and W5? Huh? E to the minus lambda? Dilek?
T.
T. Well, where does T come from? Here, I don't have any T's. Yeah. T is somewhere else. Dilek, I guess, was on the right track. What is it? 1 over lambda, which is expected value of, or the mean of an exponential distribution. So S4 is now what? Continuous random variable. So we must have written somewhere. Even we characterize actually the distribution in terms of that parameter. So it is 1 over lambda. 1 over lambda coming from here, another 1 over lambda coming from the second term, so it is 2 over lambda. Plus t, yes, that's important. Okay. Okay. And okay, any other questions about this or corrections, comments? So we can use just this property of conditional expectation, which says that you could just give to yourselves as much information as you want, in addition to what you already know, and you're allowed to do whatever calculation you think is easier to do with this additional information. But now you take another expectation from outside. Now you come back to the reality, right? So you are never allowed to use more than this, because this is the only thing that you are given, right? So this property we learned at the beginning of class, right? So perhaps we wrote over there, like, if you want to calculate the expected value of a random variable x, you can first calculate the expected value of x given y, and then you can take an expectation later. Here we started with z, then that's actually what you have added to each one of these expectations. So instead of you are taking so you are still taking the expectation, right? But now condition on it's a third random variable, if you like. So we use this thing to write this like this one. Now you can look at this. This is exactly what we meant, what we had in mind while we were drawing this picture, right? So in the first place, I was referring to W3, right? So it was like actually I knew what that is. Now that's indeed the case. So if you knew what the value of W3 was, then you can just write like what? So this W5 is in fact, what is this gonna be? So it is this remaining life after time t, so you always have time t plus remaining time until the arrival of fourth customer, which is S4 minus this difference, right? S4 minus, what is that difference? So t minus W3, right? So now we know what this is, right? Then we also have to add the next, fifth inter-arrival time. So that would be just the direct way of writing. And W5 of course equals this, right? So you are interested in the conditional expectation of this thing. So knowing some of these will not be useful because of the independent increments, and there is only it is only useful to know the value of W3 because you will need that here, and actually, and these are actually independent of both W4 and W5 because W1 is the same as S1, and we know that all inter-arrival times are independent of each other. So this really doesn't help much to say anything about or learn any statistical properties of this one. And also for this one, so S1 and S2 together will give you W1 and W2, right? S1 gives W1, S1 plus S2 gives W2, and these two are functions of S1 and S2 which are independent of S4 and S5, so we could forget about them. I just close them down. I am willing to do the same thing with W3, but then you remember that in order to be able to calculate the excess life, you need to remember what this was, right? But then we can either keep this like this, that there are exactly 3 arrivals, or you can just say that what is the equivalent way of writing then? After the third arrival, until time t, there are no arrivals, right? And that is the same as what? The fourth customer's arrival time, or the additional time until the fourth arrival, should be more than time left from third arrival until time t, right? So these two will give you these two, and they are missing here because they are independent of all these random variables. So I don't care in that case. Okay? So the inner conditional expectation can be written like this. Okay? And then what do you need to do? So once you know the value of W3, now S4 is independent of W3 because this is the sum of the first 3 variables which are independent of S4. Don't even think what happens to S5. It is always independent, so there is no even kinship closer than that, right? And then you can forget about this, and after you plug actually the number, whatever you learned from here, so maybe we could just write it like this, W3, a realization of that random variable, right? And what are you left with? First of all, we can take t outside, it's a constant, and expected conditional expectation of fifth inter-arrival time is of course independent of all this. So this is, I am supposed to do this. So from here you get 1 over lambda, right? Or maybe I should just write unconditional expected value of S5 so that we can follow from where this 1 over lambda comes. Then what do you have? So you have conditional expectation of the remaining time from t minus W3 until the fourth arrival, given that for this, well, okay, that's enough, I guess. That the inter-arrival time is already greater than t minus W3. Here we use what? Here we use memorylessness property. Of exponentially distributed fourth inter-arrival time is S4. To write, so this thing is the same as the unconditional expected value of S4. Right? Because condition on, right? So we can just write this, S4 is greater than some number S, right? Condition on that, S4 is greater than T plus S, or maybe I should just write S4 minus S greater than any number T, non-negative number. This has the same distribution as S4 itself. In other words, okay, therefore, right, expected value of this excess given that S4 is already greater than S is the same as the expected value of S4. That's, I guess we either proved this, we discussed to some extent when we were trying to solve another problem. Okay, and then we arrived to this conclusion, right? T plus the expectation of the sum of S4 and S5, which gives T plus 2 over lambda. Okay? Any questions about this? Huh? Okay. And, all right. Now, why don't I look at this uniform connection, or the connection between the uniform distribution and the Poisson that I pointed out a couple of minutes ago. Uniform distribution and its relation to Poisson process. Okay. So what we are going to see is condition on a fixed total number of events, okay, in a given interval. The location of these arrival times have the same distribution as the ordered statistics of the same number of IID uniformly distributed random variables. Okay. Okay. Let me write it in English first. I guess mathematically it is even easier to express this than just writing or telling it in plain language. But the condition on a fixed number of arrivals, right, over a given interval, given time interval, okay, the location of arrival times, okay, the location of those arrival times we counted have the same joint distribution joint probability distribution, of course, okay, as the ordered statistics of, okay, the same number of independent and identically distributed, okay, random variables which are uniformly distributed over the same interval. Over the same time interval. Okay? In other words, we would like the first, okay, I will come back to this one, what this means, okay, what we are interested in. So we are first of all given a given a Poisson process X. Okay, we know that. Okay, let us again denote the arrival times by W1, W2, and so on. Okay, and suppose that you are told that, let's say, until some fixed time t, number of arrivals equals n. Okay, and now you want to know more. You want to know more about when those n arrivals, when in the interval from 0 to t, those n arrivals land, right? So you want to know conditional, maybe I should say joint conditional distribution of W1, Wn, right? Because you are told now that there are n arrivals. Where are they? Where are they in the interval from 0 to t? Joint conditional. So this is shorter than what is supposed to be. Conditional distribution W1 to the Wn given that xt equals z. Okay? So I have time t somewhere here, and let's say on a particular realization you have something like this. You want to know the distribution or the likelihood that these n random variables are in the neighborhood of some fixed numbers in the interval from 0 to t. Right? And what the result says, what we are going to learn is that, okay, this has some connection with the unconditional distribution of the ordered statistics of n independent and identically distributed uniform random variables distributed over the same time interval from 0 to t. Okay? And we can write down an explicit formula for that. Okay? So the conditional probability that W1 is in the neighborhood of small w1 and W2 is in the neighborhood of some number W2. Okay? And finally, the nth arrival time is in the neighborhood of some given number, small wn, given that there are exactly n arrivals until time t, okay, is in fact given by n factorial divided by t the time until when we counted n arrivals to the power n times dw1 dwn. Okay? And this then turns out to be the same as another probability in another problem. If somebody asks you to calculate the probability that, okay, the smallest of, now it is not 1, you see, it is just 1 within parentheses, okay. Suppose that you are given n uniform IID uniformly distributed random variables over the interval from 0 to t. So we know what this means, right? Independently of each other, you just close your eyes and you pick a point over the interval from 0 to t, right? Arbitrarily, at random. Right? So you pick all these n numbers, and then you ask to yourself, what is the minimum of them? That's denoted by u sub within parentheses 1. Okay? So, and this turns out to be the same as the minimum is in the neighborhood of W1, and then you can, well, the second minimum is in the neighborhood of the W2, right? The same W2 matched with the second arrival time, and so on and so forth. And the nth minimum, which is in this case, of course, what? The maximum of all these n numbers, is in the neighborhood of Wn. No conditioning, no nothing. It is just plain probability, right? Okay. So this turns out to be the same as this, which we will show is the answer for this question. And then the paragraph on the left-hand side describes you this connection, namely condition, right? It says what? Condition on a fixed number of arrivals over a given interval. In this case, if interval from 0 to t, and we are told that there are exactly n arrivals. Given on that, right? The location of the arrival times, W1 to the Wn in this case, have the same joint distribution as ordered statistics. So these are called ordered statistics. You order these numbers from the smallest to the largest. They are themselves, of course, are random variables because they are functions of random variables, right? So this is then by definition the minimum of u1 to un. And this is the maximum of u1 to un. And what is this? This is the second minimum. And so on and so forth. So this is then the same as what? The distribution of the ordered statistics of the same number of, namely n numbers, n many independent and identically distributed random variables which are uniformly distributed over the same interval from 0 to t. Okay? Right. So before first of all, did we understand what is going on here? At least the statement, even though it's a little dry. Right? Okay. Before I try to convince you why this is correct, let us first see a couple of examples to perhaps convince you why such a result is important. Why would one want to or even remember such a statement at all? Okay. First couple of examples, now we'll come back and then discuss why the statement is itself correct. Okay. All right. Is there anything else that I am supposed to? What happened to my? Okay. All right. So this is again. Well, this time it is an example which is already discussed in your textbook, but I would like to just bring it here and talk together. Okay. All right. Now the question says that, well, we have a facility and customers arrive at a facility, at this facility, according to a Poisson process with rate lambda. Okay? Again, customers are coming to the facility to get perhaps some service, right? And then each customer pays $1 on arrival, so it's like an entrance fee, right? They pay up front. And then we would like to calculate the expected value of the total sum collected during the interval from 0 to t, discounted back to time 0. Okay? So we are interested in the expected present value of all future cash flows. perhaps this facility is just a bridge, right? It's the Boğaziçi Bridge. Before anybody pass through the bridge, they should just pay toll, right? So they pay not probably dollar, but I don't know how many Turkish liras, right? So if in the future you plan to sell, right, this bridge, then you will want to know how much revenue you would expect to get from this, either as a seller or as a buyer. Or if you are planning to build a new bridge, right, then you will want to know how much revenue that new bridge is going to give you, and then you will compare it with the costs. If it breaks even, then you may decide to indeed build a bridge, or just decide not to do it at all if it is not profitable. For that, what do we have to calculate? We have to calculate the expected value, because things, and how many customers, how many cars will actually come there, it's a random variable for us. We cannot really know up front. Right? So if it is indeed correct that in the future, right, cars are going to come to the bridge to cross it according to a Poisson process with a known rate lambda, and if everybody pays $1, right, so what is the expected present value of all future revenue? And as I said, okay, we will calculate that in order to make some economic conclusions thereafter, and that's it actually. Okay, anything else? Okay, just cash flow. Okay, so alright, so let us just take a short note. So customers arrive, right? Let's call it bridge now rather than a facility, right? At the bridge, according to a Poisson process with some known rate lambda, okay, and they each, right, pays, or customers pay $1 each in order to, before they cross the bridge, right? They pay $1 toll, okay, each, okay, and then we want what? We want to calculate expected present value of the future, well, revenue. I said future actually, but we will be looking only a finite horizon over the interval. Maybe we should just correct it. Let me just, over the interval from 0 to t. So maybe I shouldn't really refer to. We could also calculate actually reward over the indefinite time horizon, but this time we happen to this. We would like to find this revenue over this short period of time. Okay, want to calculate expected present value of the revenue over the interval from 0 to t. And what is this? Okay, we should be able to write this first, right? So, okay, let us first again use xt to denote the number of arrivals, right? Customer arrivals in this time interval, and let us denote by W1, W2, and so on the arrival times, their arrival times. Okay. Okay. And then I guess we can now write the present value of the tolls paid in the future, or in the interval from 0 to t, right? So customers will come like what? The first customer somewhere like before time t, the second customer, and so on, right? We have these arrivals, and at each of these times you have $1 profit or revenue you made, but then we have to calculate the present value. So let's suppose that the discount rate is known and given to us. It is just, let's call it beta, right? So $1 at time Wn, right, is going to have a present value less than whatever $1 means or can purchase today, right, because of the inflation. So that $1 has present value e to the minus beta times Wn. The time, right, when this when you receive this $1, right? So this is the present value of $1 received at time Wn, right? Namely, when the end customer arrives. So, and then the total present value, total present value of the future revenue is going to be what? E to the minus beta times Wn for each customer who arrived before time t, right? So for each customer, right, who arrived until time t, we can find, right, its arrival time Wn, at which time you receive $1, and this gives the present value. So, and this is what? Total discounted revenue that you get by maintaining this bridge over the interval from 0 to t. It's a random variable. We don't know what it is as of today, but we can perhaps calculate expected present value of revenue that we hope to receive over the interval from 0 to t. So that's what we want to calculate. Okay. Now how do we calculate this? Any ideas? Too many random variables floating around, right? Wn is over there, then there is xt. When you have too many of them, what do? You take care of them one by one. Right? Huh? Öner, you should suggest something. I don't expect an answer, but just a way to approach, or just perhaps start to drill into this hard wood. Indicator of what? What values do you think are important that I have to remember or calculate? Well, it's a continuous valued random variable. It can take any value between 0 and t. So you will have then an uncountable summation, which is bad. Probability cannot handle more than countable. No, I was just trying to convince you, well, or trying to help you spell out something else. If you knew what xt was, probably it would be easier to calculate this. You cannot even switch the order here, even if you want to do that. Right? Why don't we just first condition on the number of arrivals over time, or the number of arrivals until time t. Okay? Then we will know exactly how many customers arrived until time t. Then we will have we can calculate perhaps this conditional expectation of this funny function of arrival and arrival time easier. And actually I am going to switch from n to k. Okay? It is not important, but anyway. Right? So let us do that. So this is expected value of the conditional expectation of the same random variables, of the same random variable, of course, but given that xt, namely number of arrivals until time t, equals something. Okay? Right? I write it like this, but we can explicitly, but what this means is basically this conditional expectation, well, yes, given that xt equals n times the probability that xt indeed equals n. Right? Okay. If you prefer, we can just forget about this. Perhaps we can see the connection between these two. Right? So of course this is a value when xt equals n, So we can then calculate this. But how much credit does this number deserve? As much as the probability that this indeed is correct. Right? Right? So the fraction of time when x equals n, then I can calculate this expected value. And then, of course, I should just weight this number with this one. Right? So that's what we are doing. Right? Okay? We are comfortable with this, right? We basically condition on this value. Right? And then, okay, then we can calculate this quantity. And in fact, perhaps, but when we do that, when you know that x equals n, we can replace this, right? Because we know what it is. And in this right-hand side, we already know what it is, what this is. This is lambda times t to the power n divided by n factorial times e to the minus lambda t. We only have to figure out this conditional expectation. So is it any easier to calculate this conditional expectation than the unconditional expectation? Right away, straight forward me. Huh? Well, there we actually use that result. Now that I know that exactly n arrivals, I know that there are exactly n arrivals over the interval from 0 to t. I know the joint distribution of arrival times of these n customers. Then I should, and I know that I have actually an explicit formula for that. Then I should be able to use it to find an answer for this one. And that may suggest that actually we have to take lots of integrations, but guess what? We will not need to do that. We will actually use that. We are gonna use not this formula but this connection, namely condition on the number of arrivals, the joint distribution of arrival times, right, is the same as the joint distribution of these ordered statistics of uniform random variables. Okay? To see that, let us see that after we give a 10-minute break. Okay? So that we get some fresh air, that we can actually grasp fully all the ideas. Any questions in the meantime? All right.